This is Chapter 7, Part 2 notes. The learning objectives you see here, we will be looking at intermolecular forces. These are the forces between molecules that determine the state of matter and phase changes. We're also going to be looking at different types of solids, and then something a little bit about specific heat. And then describe energy changes that accompany these phase changes. We'll also be taking a look at heating and cooling curves. So let's jump into our topic of intermolecular forces. Hopefully you have made a copy of the fill-in notes and you can work along with me as I fill in notes and discuss. 7.7, Unit Chapter 7, Target number 7 is talking about intermolecular forces and how they relate to boiling point and melting point. So it says that intermolecular forces are the attractive forces that exist between molecules. The prefix inter means between. There is a very similar prefix, just differs by one letter. It's intra. And that means within. And so when we talk about bonds, like ionic and covalent bonds, these are the bonds between the atoms. So within the molecule, that's intramolecular. We've already talked about all of those. So now we're talking about something different. This is intermolecular, and these are between molecules. And so here we have a list of the intermolecular attractions that we're going to be discussing, and they're in order of increasing strength. So the strongest will be at the bottom. The first one is called London dispersion forces. And this is often abbreviated LDF, London dispersion forces. These are typically the weakest of the three forces, but that can vary depending on the size of the atom. Next would be dipole-dipole interactions. And then a special type of dipole-dipole interaction is called hydrogen bonding. And so the strength of intermolecular forces determines if compounds have a higher or lower melting and boiling points. It also helps determine the phase of matter at a given temperature, whether it's a solid, a liquid, or a gas. This all has to do with intermolecular forces. Intermolecular forces are often abbreviated IMFs. So let's take a little closer look at London dispersion forces. So London dispersion forces are very weak interactions, and they are due to momentary changes in electron density. The change in electron density creates something called a temporary dipole. The weak interactions between these temporary dipoles constitutes the London dispersion force, or the LDF. All covalent bonds all covalent compounds, I should say, have London dispersion forces. In fact, not just covalent compounds, but all compounds have LDFs. So let's just change that. That is not even right. All compounds. So no need for this blank here. All compounds exhibit London dispersion forces. We could add a little note here. Non-polar molecules only have LDF. So sorry for that mistake there. Nonpolar molecules, the only type of interaction they have is LDF. But all compounds, all molecules can have some form of London dispersion force. The larger the molecule, the larger the attractive force, and the stronger the intermolecular forces. All right, now that we have the words down, let's look at what this LDF attraction is. So I have some pictures here that hopefully will show it. This is a little bit difficult to grasp maybe. We know that atoms have a nucleus in the center, and then surrounding the nucleus are electrons. And these electrons are in constant motion. And so when in our notes when we said that we had a change in electron density, just suppose that all of the electrons within the molecule ended up on one side of the atom, as you see in this picture. These are all of the negative signs here are on one side of the atom. If that happened, that would create something called a dipole. A dipole is simply when you have different charges on different sides of the atom. So a pole, think of a magnet, like a bar magnet has a north and a south pole, and so that is called a dipole. The atom doesn't have north and south magnetic poles, but it can have different sides of the atoms can have a positive and a negative charge, and so that is also called a dipole. And so back to this LDF, if the electrons of one atom end up on the same side of the atom for a temporary amount of time, that would make that side of the atom slightly negative because of this high density of electrons, and the opposite side of the atom would be slightly positive. And since these aren't permanent charges, or since these are not permanent, we assign them a special symbol, and so you see it drawn here. This is the Greek letter, the lowercase delta, and it looks like a kind of a fancy little S, and it means partial. So we have a partial negative side and a partial positive side on the other side, and so those are our two poles. Here's the negative side and here's the positive side. And so it's showing here that more electrons are on the negative side and less on the positive side. Well, if this came in contact with another molecule, it could create a temporary attraction. It could, so this positive side, right here, all of this positive side, slightly positive side of this atom, molecule, would have an attraction for the other atoms electrons, and so it would pull all of the electrons to that side, and it would create a dipole in this second atom as well. So since all the electrons have been pulled away, this side is going to be slightly positive, and so it's kind of like a domino effect, if you will. It is a temporary dipole, a temporary attractive force. We know the electrons are in constant motion, so it doesn't last long, but it is enough of an attraction to hold molecules together. All right, let's talk about the second type of intermolecular attraction, and that is the dipole-dipole attraction. Dipole-dipole attractions are the attractive forces between permanent dipoles. So unlike the LDF dipoles, these are permanent, meaning they're always there. They don't fluctuate. They don't. It doesn't matter if the electrons move around. The dipole is still there. And this always happens between two polar molecules. So both of the atoms have to be polar for a dipole-dipole interaction to take place. And so we have two examples here, or we have an example of a dipole to a molecule of formaldehyde, so it's drawn out structurally here. And then we see that they have added the charges on the ball and stick models, the slightly positive end here and the slightly negative end here. And the reason that this is slightly negative is because oxygen is has a higher electronegativity value than the remaining part of the compound, so it's drawing the electrons toward the oxygen, and so that makes for a polar molecule. And so if we had a molecule of formaldehyde near another molecule of formaldehyde, you can see that their opposite poles would be attracted to each other, and so we would draw an attraction with using dotted lines like that. The negative end of one molecule is attracted to the positive end of the other molecule. This is referred to as dipole-dipole interactions. And then the third IMF that we will discuss is hydrogen bonding. It says hydrogen bonding occurs when a hydrogen atom is bonded to either oxygen, nitrogen, or fluorine, and is electrostatically attracted to oxygen, nitrogen, or fluorine in another atom or another molecule. So hydrogen bonding is a special type of dipole-dipole attractions. This is a permanent dipole. The most common example that you see is water. Water is a polar molecule, and the hydrogen in water is bonded to oxygen, and that was one of our criteria. We had to be bonded to either oxygen, nitrogen, or fluorine, and this hydrogen is bonded to oxygen. So in one water molecule, the oxygen could be, or the hydrogen of one atom could be attracted to the oxygen of another. And so you see here it's pointing out the hydrogen bond. This actually has an unfortunate name. The name has bond in it, so you think it's a normal bond, when in fact it is not. It is just a molecular attraction. So it's not as strong as a bond. Hydrogen bonds are the strongest of these three types that we've talked about. LDF being the weakest, dipole-dipole somewhere in the middle, and then hydrogen bonding is the strongest of these three. We'll see on the next graphic that hydrogen bonding is important in our DNA. We know that the DNA is in the nucleus of our cells, and that determines everything about us. The DNA is made up of nitrogenous bases on the backbone of the DNA molecule, and the connection between the nitrogenous bases is a hydrogen bond. So this graphic is pointing out where those hydrogen bonds are. So anywhere you see these dashed lines or dotted lines, these are hydrogen bonds. So very important in our chemical makeup for sure. This next little table here is a good summary of the three types of intermolecular forces, and so it would be good to study these. Relative ratings or strengths, meaning relative to each other, and this exhibited by tells what type of molecules exhibits each of the three types. And notice it says London dispersion is found in all molecules. Dipole-dipole is between two polar molecules, and then hydrogen bonding has to have a hydrogen, of course, and that hydrogen has to be attached to either oxygen, nitrogen, or fluorine. All right, let's look and see how these IMFs affect the boiling and melting points. And so we see that the boiling point, of course, is the temperature at which liquid is converted to the gas phase. And as you already know, melting point is the temperature at which a solid is converted to the liquid phase. The stronger the IMF, the higher the boiling and melting points. So this is something to remember for sure. This is a relationship between IMFs and these phase changes that we're talking about. The stronger the IMFs, the higher the boiling and melting point. We can see two examples here on our next slide. We have methane. Methane is a nonpolar molecule, only has LDF forces attracting multiple methane molecules together. And so we can look at its melting and boiling points and see that they are very low. So negative 162 and negative 183. On the other hand, we have water, which is a polar molecule, and also has a hydrogen bonded to an oxygen. So there are hydrogen bond attractions between water molecules, and we can compare the boiling and melting point and see that they are much higher than that of methane, and that is because the attraction between the molecules are very strong compared to the other. Here's another example of two nonpolar molecules. Both of these are hydrocarbons. We have propane and butane. Propane only has a 3-carbon backbone chain, where butane has a 4-carbon. So it says longer molecules have stronger forces. That would be good to remember. And therefore higher melting and boiling points. And we can see that reflected here in the numbers. So we've talked about melting and boiling. There's also some different terms that we can apply here. So evaporation is a conversion of liquid into gas. And this is an endothermic process, which means that it absorbs heat. So if we want to turn a liquid into a gas, we have to add heat to that liquid to break the intermolecular attractive forces so that it can turn into a gas. So it will absorb heat from its surroundings. On the other hand, we have condensation. And condensation is turning a gas back into a liquid. And this is an exothermic process. Exothermic means that heat is given off to the surroundings. And so to change from a gas back to a liquid, we have to cool the substance down. And so heat has to be removed from the substance, and that is exothermic. Another word that you'll come across is vapor pressure. Vapor pressure. So it says that a vapor pressure is the pressure exerted by those gas molecules when it's in equilibrium with the liquid phase. So in this picture, we see that we have liquid gas here, liquid water here, and then at the top of the circle there is some water molecules that have turned into a gas. And when you have a closed system like this, the gas on top is going to exert a pressure on the liquid below, and this is called vapor pressure. And so in order for these other liquid molecules to turn into a gas, they must overcome the vapor pressure. And so vapor pressure increases with increasing temperature. And as I said, the boiling point of a liquid is the temperature at which its vapor pressure equals the atmospheric pressure. So we talked about gases in the last part of Unit 7, first part of Unit 7. And so you know that this is standard pressure. And so in order for something to boil, it has to overcome the standard pressure, or the pressure wherever the liquid is. Let's go on and look a little more at vapor pressure. It says the stronger the intermolecular force is, the lower the vapor pressure at a given temperature. So when I teach my students about vapor pressure, I like to think about gasoline. When you go to the convenience store and you put gas in your car, as soon as you open the gas cap on your car, especially if it's a warm day, you can see the gas fumes coming off immediately. And that is because gasoline turns into a vapor very easy. Gasoline has a very high vapor pressure. That means it doesn't take a lot for the liquid to turn into a vapor. So this statement here that says the stronger the intermolecular force is, the lower the vapor pressure. So the intermolecular forces between the gas particles is not very strong, and so it turns into a gas very easily. On the other hand, if you have something like water, it takes a lot to turn water into water vapor. That is because there are strong intermolecular forces and water has a low vapor pressure. So that can be confusing sometimes. So if you'll just remember this idea of gasoline having a high vapor pressure, then you can maybe understand that other things are much lower. So that may help you with the difference between high and low vapor pressure. Just remember, high vapor pressure turns into a vapor very easily. A couple of other words that we can use to describe liquids are viscosity and surface tension. So viscosity is a measure of the fluid's resistance to flow. Resistance to flow freely. Honey would be an example. It would have a high viscosity. It doesn't flow very freely. So a viscous liquid feels thick like honey. Compounds with strong intermolecular forces tend to be more viscous. Substance composed of large molecules tend to be more viscous. And then let's look at surface tension. So surface tension is a measure of the resistance of a liquid to spread out. This is an interesting definition. I've not thought of it this way before. Surface tension, you've probably seen a little spider on the top of the water, running across the top of the water. Or maybe you have attempted to float a paper clip on the surface of water. Water has a very high surface tension, and so it's holding the molecules together, resisting the urge to spread out when pressure is put on it. And surface tension has to do with the intermolecular forces, just like viscosity. So the stronger the IMFs, the stronger the surface molecules are pulled down toward the interior of the liquid, and the higher the surface tension. So the stronger the IMFs, the higher the surface tension. Water has a very high surface tension because of its strong IMFs. And like the paper clip, small objects seem to float on the surface because they're held up by the surface tension. All right, let's talk about the solid state. So we started talking about the gas state. We spent a whole week on gases. This first part we talked about liquids, and now we're going to talk about solids. So there are two basic kinds of solids. They can either be something called crystalline solids, or they are called amorphous solids. So these are the two classes of solids. A crystalline solid has a regular arrangement, like a repeating pattern to its arrangement of atoms or molecules, with a repeating structure. So a regular arrangement with a repeating structure, that would be crystalline. And there are 4 different types of crystalline solids. There's ionic solids. There are molecular solids. There are network solids. And there are metallic solids. We'll go through examples of each of those. And then on the other hand, amorphous solid has no regular arrangement. So there's not any kind of repetition in an amorphous solid. And we'll look at an example of that as well. All right, first of all, the ionic solid. So think of any ionic compound, any kind of salt. And this is a picture of sodium chloride. It's composed of oppositely charged ions. Remember, we have cations, like the sodium ion, and we have anions, like the chloride ion. So this repeating pattern of positive and negative forms what's called a crystal lattice. And this is a crystalline solid. We can also have a molecular solid. So we tend to call these covalent compounds. Think of water or sugar. There is an arrangement, a repeating pattern, but instead of ions, we have molecules. And so if you take a close look at this picture, you can see that there are water molecules that are attracted to one another, held together by those IMFs. And if you take away enough energy from that, you can create a solid. And we would call that ice. We have something special, a special kind of covalent compound called a network solid. The example that they're showing you here is sand, silicon dioxide. A network solid is composed of a vast number of atoms that are covalently bonded together. And so instead of just having intermolecular attractions, like in the picture of the water molecules, these are actually held together with bonds. Another example of this is a diamond. A diamond is made of carbon atoms. It's all carbon atoms. And the carbon atoms are held together with covalent bonds. Very, very strong solid. Very difficult to break. And then lastly, our crystalline solids, we have metallic solids. And so these are just our metals. This is showing copper atoms that are bonded together through a metallic bond. You could also think of maybe a piece of aluminum foil where you have a bunch of aluminum atoms that are being held together. And so these are the 4 types of solids: ionic solids, molecular solid, network solid, and metallic solid. And each of these has their own different properties. Then we have our amorphous solids. And again, we are saying that they have no regular arrangement to them. They can be formed when liquids cool too quickly for regular crystal formation to happen. Very large covalent compounds tend to form amorphous solids because they can become folded or intertwined. some examples. We have rubber, like the rubber on your car tires, or glass, or even plastic are examples of amorphous solids. So the main difference between the two is that crystalline solids have this repeating pattern to them, and amorphous solids do not. All right, let's talk about specific heat for a moment. So specific heat is the amount of heat energy needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. The amount of heat energy needed to raise the temperature of 1 gram of a substance 1 degree Celsius. This is called specific heat. The larger the specific heat, the less its temperature will change when it absorbs a particular amount of heat energy. So water has one of the highest specific heats. Water's on our list. So we see that liquid water has a specific heat much higher than everything else on the list. So 4.184 joules per gram degree Celsius. For everything else, the next highest one to it is propanol, which is a type of alcohol. So water has a very specific heat, and it's one of the reasons why water is used to put out fires. Is because it can absorb a lot of the heat energy from the fire, and so it makes a good tool to put out fires. We can use this idea of specific heat to do some calculations, and so you might see a question like this. It says, how many calories, energy is measured in calories, how many calories are needed to heat a pot of 1,600 grams of water from 25 degrees to 100 degrees. And so we want to first start by identifying our unknowns and identify our knowns, and our unknown, what it wants us to solve for. So as we read through the problem, we see that it gives us a mass equal to 1,600 grams. It's telling us that the initial temperature is 25 degrees Celsius, and the final temperature is 100 degrees Celsius. And it wants us to find out how many calories of energy is needed to make this water heat up. So we're not going through a phase change, we're simply just heating the water up from 25 degrees to 100 degrees. It does give us some information about the specific heat of water in terms of calories. So it's 1 calorie per gram degree Celsius. The equation that we're going to use is Q equals mc delta T. And let's just go through the variables here. Q is the symbol used for the heat energy. And then we have M, which is the mass in grams. We have a capital C, which is the specific heat. And then we have delta T, which is always the final temperature minus the initial temperature. So if you look at this equation, we call this the MCAT equation. So the MC delta T looks kind of like MCAT. So that's a way to remember the equation. And once you have all of your known quantities written down, then you're ready to solve the equation. So we had Q is equal to mc delta T. So here's our M. Here is our specific heat, C. And then the change in temperature, 0 minus 25, gives us 75 degrees Celsius. And so we have an answer of 1.25 times 10 to the 5th calories. For some reason my calories got moved over here. So the unit here would be calories. 1.25 times 10 to the 5th calories. So this number is written in scientific notation. It just means that their decimal place has been moved 5 places to the left. So this is a very large number. A lot of energy is needed to heat up water. So the amount of energy needed to melt 1 gram of a substance is called the heat of fusion. The heat of fusion. And so we can also solve problems involving heat of fusion. So here's an example. It says how much energy in calories is absorbed when 50 grams of ice cubes melt. The heat of fusion of water is 79.71 calories per gram. So we want to identify what we've been given and what we are asked to solve for. So we know we have water and that the mass of that water is equal to 50 grams. And it's asking us for the calories, how many calories were needed. It gives us the specific heat, has 79.71 calories per gram. So we can use this as our conversion factor. And so if you remember, we can always write 2 different conversion factors for every equivalent. And so we have 1 gram on top and 79.71 calories on the bottom. Or we can flip that and put 79.71 calories on top and 1 gram on the bottom. Then if we I think there's a typo here. It says cancel the unwanted unit milligram, but we're not given milligrams, so just mark that out and put gram. And so if we want to cancel out gram, we know that we want to choose the conversion factor that has gram on the bottom. You'll remember from our previous workings with conversion factors. And so then we would just solve the problem. So the our starting amount was the 50 grams of ice. And then we're going to use our conversion factor that has gram on the bottom so that grams cancel. And then we just have 50 times 79.71. Our final answer should have 3 significant figures, so we would round our answer to 3990 calories. So that would be our final answer. So this was called the heat of fusion. And then if we look at the other end of our heating curve, the amount of energy needed to vaporize a gram of a substance is called the heat of vaporization. So to turn a liquid into a gas, you have heat of vaporization. There's also a phase change that you may or may not have heard of before called sublimation and deposition. And so sublimation is where you have a solid, this is the solid, that turns directly into a gas without passing through the liquid state. So an example of sublimation would be dry ice. Maybe you've had some experience with dry ice before. So dry ice sublimates very easily. When you put the solid on a table, it starts turning into a vapor immediately. And then going the other direction from a gas directly to a solid is called deposition. So these 2 terms you need to be familiar with, sublimation and deposition. So the next page has a summary of all the different phase changes, and it also indicates whether it's endothermic or exothermic. So this would be something that you should study. You should know all the different names of the processes, and then whether it is endothermic or exothermic. So be sure and look over that chart. And then here we see a graph that's called a heating curve. The first one is a heating curve. And so it says a heating curve shows how the substance temperature changes as heat is added. And so we can see from segment A to B, the temperature is increasing. Temperature is on the y-axis. So as I go from A to B, the temperature is increasing. But as soon as I get to point B, all the way to point C, even though I'm adding heat on the x-axis, notice that it says heat is added, even though I'm adding heat, the temperature is not changing. So what's happening during this melting phase is all of the intermolecular forces are being broken, and so all of the energy is going into breaking the IMFs so that the substance can melt. And as soon as everything has melted, you'll be at point C, and then as you go up to point D, the temperature is increasing again. And then at point D to E, we have another phase change called boiling, so changing from a liquid to a gas. And again, energy is being added the entire time, but instead of the temperature increasing, all of the energy is going into breaking the intermolecular attractions. And so the temperature stays the same until all of the liquid has turned to a gas, and then the temperature can increase again. So when we were looking at our equations a moment ago, anywhere that the temperature is increasing, to calculate the energy, for example, from point A to point B, you would use the MCAT equation. So Q equals MC delta T. So you would use it anywhere. I call these the slants. So from A to B, from C to D, you would use the MCAT equation. And from E to F, you would use MCAT equation to calculate the amount of energy needed to make that change. Now when the temperature is not increasing, you can't use MCAT because there's no change in temperature. So on the flats, so from B to C and D to E, you have to use a different equation. So that's Q is equal to, you can either use moles or mass, and then you multiply it by the delta H. So for this one, it would be the delta H of fusion, and for the top D to E, it would be Q is equal to the moles times the delta H of vaporization. So those are two of the examples that we did earlier, and this is how they apply to the heating and the cooling curve. So the cooling curve is on the next page, and it's just the same. It's just written in the opposite direction. And so the cooling curve, as you see, shows how the substance's temperature changes as heat is removed. Heat is removed. Okay, so as I'm cooling down, heat has to be given off. So a cooling curve is exothermic. Heat is having to be released. And the heating curve is endothermic because you're constantly adding heat. And so we have the opposite processes here. Instead of boiling, we have condensation. And instead of melting, we have freezing. All right, that concludes unit chapter 7, the study of solids, liquids, and gases.